Enjoy yourself.
Yeah.
That's the negative, but if we
Right.
And at first, at first we were like, oh, okay. I mean, all the fish are sick, but one I don't have. You know, no, that is also true.
Yeah.
That's definitely true.
Yeah, that shouldn't be showing. So that I don't understand.
It-
Okay,
agree.
mathematicians. So I have a
But
small
this is-
problem.
Okay, what's that?
Get the Zoom thing to stop showing. Why is it doing it? Really?
No, usually
Usually it goes away.
Usually it goes away.
Can you move it to the left? If you grab the
Yeah,
green thing.
grab it and move it.
Yes.
Go away.
Like if you push it to the left side and then you go.
Oh.
Oh.
What happened?
Let me see. Let me see if I can. It's supposed to go away afterwards. It's supposed to just go away.
Yeah, that works.
Like real problems, just ignore it. It does exist.
Beautiful.
Okay.
Is it recording?
And let's do this so you don't, and watch the wires. That's the only
This
thing.
recording.
Oh, it's definitely recording, but watch the wires. That's the big thing. Like careful, totally careful. Okay, so sorry about the chaos, everybody. All right. Who's going, should I interview? I'm interview.
Good. You're the organizer. Go for it, Marta.
So greetings, everyone. So I am happy to welcome Marta Pavelka. I hope that's correct pronunciation. She's visiting from the University of Miami for the next few days. And today she's going to be speaking about 2LC, triangulated manifolds, or exponentially many. Take it away. Thank you.
Thank you for the introduction. Thank you all for coming for my talk. So I would like to share with you some new findings we got with Bruno Benedetti, who's my advisor, about triangulations of manifolds. And you can also find all the proofs and details in our paper of the same name, in case you get curious. So let me start by covering the background picture to make sure that we are all on the same page with some simple complex terminology. We call facets the inclusion maximum faces of the complex. Pure complex has all facets with the same dimension. Star of phase sigma is the smallest subcomplex containing all facets that contain sigma. So if you look at the picture in the corner, that's a two-dimensional simple complex. It's formed by triangles. And if we want to know what the star of the vertex B is, that's just formed by all the triangles containing. Link of sigma, phase sigma, would be formed by all the faces of the star that do not intersect sigma itself. So in the picture again, if we want link on the vertex B, that would be formed by all the edges on the boundary of the star, because those are in the star, but they don't touch a B. Okay? We will need the notion of the link quite a bit, so that's why I want to make sure that by a triangulation of a smooth d-manifold, we mean a d-dimensional simplicial complex whose underlying space is homeomorphic to that manifold. And there's one important fact from algebraic topology that we use a few times, which is that links in triangulated manifolds are always homology spheres or homology balls. So we will. By a d-sphere, I mean a triangulation of the d-dimensional sphere. And by a d-pseudo-manifold, we mean a d-dimensional pure simplicial regular CW complex, where each d-1 cell is in at most 2 facets. So in a pseudo-manifold, if you have 2 triangles, say they are in dimension 2, the triangles can share an edge, that's fine. But if there would be a third one, if we have 3 of them, sharing the same edge, that is an issue. This will not happen in a pseudomanifold. Okay. So the question, how many triangulations of the free sphere with n tetrahedra are there, has been around for a while. Actually, Gromov listed it as one of the fundamental questions of topology. And notice here that we fix the dimension and we are counting in the terms of the number of facets. That's the capital N. And there has been a lot of work done trying to find upper and lower bounds for the number of spheres and polytopes, actually, in the terms of the number of vertices. There's this famous upper bound by Stanley, and for instance, Macaulay constructed for an exponential many triangulated spheres, and so on. There is a bunch. But these bounds in the terms of the number of vertices do not give us any interesting bound in the terms of the number of facets. Luckily for me, because that's what I'm working on. So two triangulations are equivalent for us if they have the same base coset. And particularly what we're interested in is whether there are exponentially many of these triangulations or more. So what does that mean? Say we have a class, let's call it A, of manifolds or pseudomanifolds, and we say that it has exponential size, or the same thing, you could say that there are exponentially many. There are several ways to say it. If there exists a constant such that the number of manifolds or pseudomanifolds in this particular class with n facets is at most p to the power of n for every n. So the constant here is universal with respect to the number of facets. That's what it means to have exponentially large class. If there's no such constant, we say the class is super exponential, or that there are more than exponentially many. So all these terms again mean the same thing. And this particular exponential question comes from physics, from so-called discrete version of quantum gravity, where they have a model coming over all triangulations in a certain class. And it happens to converge only if the class is exponential large. If it's bigger than exponential or super exponential, the whole model collapses and it does not work. So there has been a search for classes of exponential size. And it's not a trivial task already in dimension 2, because it's actually fairly easy to construct more than exponential many surfaces with n triangles. And I would like to sketch a proof of this. So, right here. The plan, what is the plan? We fix number g, just an integer, and we will construct g factorial surfaces with genus g, and then we connect g with capital N, which will give us more exponential surface. So that's the plan. How do we do that? Is that we start with such a strip of triangles that you can see on the slide. And notice that there are two G triangles that are labeled 1, 2, all the way to G, and then it repeats 1 prime, 2 prime, all the way to G. Next step is to cone over the boundary of this strip, just the boundary. And when we do that, we get a two-sphere. So let's pretend this is the two-sphere. What are we gonna do now? We're gonna remove all the interiors of the labeled triangle. So we get two G folds. Fold number 1, fold number 2, all the way to G, and then 1 prime, all the way to G prime. Next, we're gonna fix a bijection. Let's call it pi, and we fix it. Bijection from the set 1 to G to the set 1 prime, 2 prime, all the way to G prime. And it's a bijection, that's important. So we have G factorial options here, how to choose. Okay? Okay, we have this bijection, we use it now to fill in these holes with handles. So we attach handles from the hole I to the hole pi of I for every I. And we want everything triangulated, so we just triangulate these handles. I think you need 6 or 8 triangles to work. There's just some nice small number. Okay, so what we constructed here, we constructed a surface of genus G with capital M is 14G plus 5 triangles. This number is not obvious at this point, but it's very easy just to like count the triangles at the beginning and along the construction. You add some triangles that happening. And this is the number you will get. But this we got just for one fixed bijection, but as I said, we can do it for any, right? So we have this map from all the permutations on G elements to this type of surfaces. The key thing here is that not only we can go this direction, but we can also go back. So the way to do that is if you give me a surface of this type, what I'll do, I'll find the vertex that has the highest degree, and that's going to be this guy. We know it's the one we count over with. And so I will look at the link, and the link is exactly the strip. And then off of the strip, we can read the bijection. So not only we can go this direction, but we can also go back, which means that there are G factorial of these surfaces. And since the G and N are connected with this relation, this means it's also more than exponentially many in N. So there will be no constant such that the number of the surfaces within triangles is less than e to the n for every n. We will not find the term. Any questions?
So this extra triangle to were labeled, those have to make sure that you can go backwards in that direction.
Yes.
Okay.
Yeah. Exactly. So as it, any other question? So as a consequence of this, what we can do, we can take each of these surfaces we just constructed, we can cone over them. And that way we get more than exponentially many 3 pseudomanifolds within tetrahedron. And we just jump from manifold to pseudomanifold because if you imagine what's happening, we have the surface with all the handles, we cone over it. When you look at the length of this vertex, it's the surface that is definitely not a homology wall. So we will not receive a manifold, but we will have to. So this is the conclusion we can make. And now I would like to explain what are the locally constructible manifolds. So to construct a manifold using local construction, we need to start with a tree of d-simplices. And this pretty tree that you can see is what Google thinks a tree of tetrahedra looks like. But that's not what I mean by it. So for us, a tree of d-simplices is just a triangulation of a d-ball whose dual graph is a tree. So this would be an example. In dimension 2, I have a little model of it here where you can see the dual graph and it's a tree. The dual graph just means that you put a vertex in each facet that you connect two vertices if they share a codimension one. Okay, so this would be a tree of triangles. Once we have such a tree, we recursively glue to adjacent boundary facets. In other words, we can glue to boundary facets if they share a codimension one face. So for instance, one way to get a two-sphere out of this tree using locally constructible gluings is first to perform the green gluing because the green edges pairwise already share a vertex, so they are adjacent, and you will receive something like this. This guy is still open. And then by performing the green gluings, what happened is that these blue edges became adjacent and these red edges became adjacent. So in the second round, we can finish the construction by going together and we get a two-sphere. Two things to notice here. First one is that once we glue two boundary facets, they sink into the interior, right? We cannot use them again. They are done for the construction. And also, if we perform a gluing, the situation changes, right? New adjacencies can arise. And so after each gluing, we need to check again what the situation is. So this adjacency condition is dynamic. That's what we call it. In a similar way, we can define Mogami manifolds. There we can glue two boundary facets if they share at least a vertex, regardless the dimension. So just to make sure we can see the difference, say we have a tree of 10-dimensional simplices. Okay? The boundary of this tree will be 9-dimensional simplices, and we can glue them together. If we want locally constructible manifold, we can glue them together if they share 8-dimensional face. If we want Mogami construction, we can glue them together if they share at least a vertex, even though they are in dimension. Okay, is the difference clear? Wonderful. Next thing to notice is that these matching arcs in the picture, they do not intersect. And it's not a coincidence, it's actually important observation because these are called planar matchings. And they are actually, the number of them is bounded by, or is counted by Catalan numbers, which are bounded by exponentially. So that's something very useful. And we can also see why they cannot intersect. So let's imagine we would perform a gluing that is not planar. These two gluings, right, they intersect. Let's have a look at what's happening with the blue point. So this blue point will end up on different hemispheres of the final two-sphere, as suggested in the picture. But at the same time, we just glue them together, right? They are the same point. This cannot happen in a two-sphere. So non-planar gluings are not allowed. And I have two more things I want to say here, and both of them are about connected d-dimensional manifolds. So the first thing is that we know that every connected d-dimensional manifold has connected dual graph. So I'll make a picture in dimension 2. Say this is our manifold. So if we say in dimension 2, there are a bunch of triangles in it. And what we know, if we take the dual graph, which will look there, we know that it's connected always. Therefore, we can find its spanning tree. Right. Okay, this one. Draw one real quick. Okay, this is our spanning tree. Then what we can do, we can actually unglue the manifold, right? This thing is not pierced by the tree, and we can unglue these two triangles. We can do that for every such thing. And therefore, we, at the end, get a tree of simplicity. And we can reverse the process. We can get that tree and reverse the gluing process to get back the original manifold, right? The gluings, though, they don't have to be LC or Mogami. They might be disconnected from far away, but there will be a series of gluing for every connected manifold. At the same time, though, we know that there are more than exponentially many of connected manifolds. So if we allow any gluing, if we put no restriction, we get super exponential class. But if we restrict ourselves to the LC thing, we know that what we can get is only exponential class. of manifolds. Durhuus and Jonsson show this for dimension 3, and Benedetti-Ziegler generalized it to all dimensions. So they show that LC triangulations of d-manifolds with n facets are at most 2 to the least squared. And this was actually an important proof for polytopical theory, because every polytope has shellable boundary. Everything that is shellable is locally constructible, so this bound actually also works for polytopes. And it was the first proof that there are only exponentially many polytopes in the terms of the number of facets. So it was a big deal. And their proof also works for LC pseudomanifold, no modification. Moreover, Mogami showed he is a physicist, so he used language that physicists only can approve of, but he showed that Mogami triangulation of 3 manifolds with n facets are exponential. He didn't even give us the precise constant, but also he worked in dimension 3 only. Okay, so that's a thing. So as I suggested before, there has been a search for classes of exponential size. And another example in dimension 3 are, for instance, so-called polar triangulations. Those we get by slicing a manifold and triangulating each slice separately. An example in general d-dimension would be triangulations with bounded geometry, and those are defined with metric stuff. So they bound the volume, diameter, this type of properties. But the main point I want to make here is that all the classes that I mentioned have characterization using this discrete Morse vector, actually bounded discrete Morse vector. So they are all in this class of triangulations with bounded discrete Morse vector, which is also only exponentially large. And the only class that does not have that characterization is the Mogami class. There might be characterization, but we don't know of one, and it's not for lack of trying. So that makes it interesting, this class. And so today, what I will do, I will introduce a new class, a class that contains the LC class that I just introduced, and extends Mogami's intuition to all dimensions. So we got this idea to generalize the LC notion based on the dimension of the intersections of the boundary facets that we glue. And that way we kind of filled in the missing pieces of what was already explored. And so we defined a movie. We defined TLC d-manifolds as those obtainable from a tree of d-simplicity by recursively gluing two boundary facets whose intersection has dimension at least d minus 1 minus 2. So let's explore this definition. Let's see what it gives us. Let's start at the beginning of the movie. Let's take t equals 1. 1 LC d-manifolds are obtainable, blah, blah. Intersection has dimension at least d minus 2. So we have d-dimensional tree. The boundary has dimension d minus 1. We can glue it if they have intersection d minus 2. This is exactly how we define the locally constructible class. So 1 LC or LC. Next will be 2 LC manifolds, 3 LC, and so on, until we hit d minus 1. Okay, so let's see what those are. If we take d minus 1 LC, those are manifolds, blah, blah. Intersection has dimension at least d minus 1 minus d plus 1 with 0. Right? 0 dimensional intersection, just a bunch of vertices, or most probably one vertex, right? So that's exactly how we define the Mogami class. Okay, Last one, the end of the movie would be T equals D. So DLC, for those, we get the intersection at least -1 dimensional, which in our convention means that we don't require any intersection. And as we saw, that way we can get any connected d-manifold. So this notion interpolates between LC and connected d-manifold. And also, thanks to this, at least in the definition, we know that these classes are nested. So we get this sequence of nested classes. Therefore, if a manifold is 1 LC, it's also 2 LC, 3 LC, 4 LC, and so on. And at the beginning of this sequence, we have a class that has only exponential size. At the end, we have super exponential class. So somewhere along the way, this property has to break from exponentially many to more than exponentially many. And what we managed to show is that it is safe to take one more step. We showed that 2 LC triangulations of d-manifolds with n facets are at most 2 to the d cubed over 2 times. And we also believe that this is the last step one can take. We believe that the 3 LC are already more than exponentially many. So regarding pseudomanifolds, what we showed is that if we cone over a TLCD pseudomanifold, it stays TLC. So why is this interesting right now? It's interesting because at the beginning, we constructed all these surfaces, right? So we had 2 manifolds. It was more than exponentially many of them. And they were all connected. Therefore, they were also all 2 LC. And so we can take those and cone over, as I did at the beginning, and we got more than exponentially many. The 2 LC stay, and we get 3 pseudomanifolds. And we can code again. We get more than exponentially many 2 LC, 4 pseudomanifolds. We can code as many times as we want to. The conclusion is that there are more than exponentially many 2 LC d pseudomanifolds. So there's no exponential bound for them. There are way too many, which indicates that our bound is not a straightforward extension of the Benedetti-Ziegler one, because for us it's crucial to have a manifold. Without that assumption, it's false. We cannot have a bound. And you might be curious, I hope you are, what were the properties of manifolds that we used and pseudomanifold miss? Right? The short answer is nice links. Let me elaborate a little. So in the definition of 2 LC, we can glue 2 bounded facets if they share a d-d. So for 2 LC, we need to have common d-3 things. And in the final manifold, again, the d-3 phase will have a link. Okay? The link. What do we know about this link? First of all, it will be 2-dimensional. 2-dimensional, and it has to be a homologous sphere or a homologous ball. However, in dimension 2, we can just don't. So the link will actually be either a 2-sphere or a disk. It depends if we're on the boundary or. So it's a very strong property for the link, and that's something that we use to establish which gluings can lead to a manifold and which not. Based on that, we're able to bound the number of them, using also the fact that the planar gluings are counted by Kaplan numbers. So that was another important part. And this is just very like small peek into the whole problem. We needed to deal with a lot of tedious details along the way because the construction does not really preserve all the nice properties. We will not have simple complexes along the way and so on. And I have an example to show you what kind of issues one has to deal with. So in a simplicial complex, if we just have a simplicial complex, we also have a one-to-one correspondence of the edges on the boundary of the length of a d-3 base and the boundary facets containing it. So in the original tree, which is a simplicial complex, this will be the length of our d-3 base. It's going to be a triangulated disk. And each edge on its boundary corresponds to exactly one boundary facet containing this face sigma. So in the same way, there's one-to-one correspondence between a gluing of two boundary facets with respect to sigma and gluing two boundary edges in the length of sigma. Okay? So that's a very nice thing that we used, however, is true only for simple complexes. So it works basically only for the original tree. Because once you start the locally constructible or two locally constructible construction, so once you start it, you will lose, for instance, you will not have a manifold right away. Imagine we glue these two edges together. This length becomes something that is not a homologous sphere or ball. Therefore, we are out of the world of manifolds right away. But we also leave the world of simple complexes really fast because you will start seeing intersections like this after just a few steps. So this would be two triangles sharing not only an edge, but also a ring. And that's not allowed anymore. So along the way, we have pseudomanifolds, CW complexes, and all the nice properties that we have in simplicial complexes do not work there necessarily. And I also have an example here of two properties that a gluing has to have in order to even have a chance to lead to a manifold. And those are the nicest one to illustrate. The first one is orientability. So imagine that we would take this bottom edge, we would flip it and glue it. We would lose the orientability of the length. And this cannot be fixed with any further gluing. So this cannot happen because at the end, this thing has to be a homologous sphere. It has to be a sphere actually, or a disk. So non-orientable gluings cannot perform. And the second example we actually already saw, there's the planarity of the matching arcs, right? So the explanation here is exactly the same. Non-planar gluings are not allowed for the exactly same reason. But the one thing I want to mention here is that in this argument, we are secretly using this really simple to see theorem, but really, really difficult to prove from topology. It's called Jordan-Shenfield's theorem, and it says that if we have a sphere, we can divide it into two hemispheres with a circle. It sounds trivial, but it's actually very complicated to show. Okay, in the last 20-ish minutes, 15, I have one more picture I would like to share with you all, and I will also turn it into a movie, but before I do, let me just recall these two definitions to make sure we can all follow. So a d-dimensional complex is called Cohen-Macaulay if for any face and for all i's less than the dimension of the length of this face. And the I homology group is trivial. And in the same way, we can define homotopy, Cohen-Macaulay, by just replacing homology groups with homotopy groups. And as usual, the homotopy, Cohen-Macaulay, will imply the homology case, the regular Cohen-Macaulay. Now, the second definition is constructible simple complex. That's defined inductively. Every simplex and every zero complex is constructible. And by zero complex, I just mean bunch of points, vertices. A d-dimensional pure simple complex that is not a simplex is constructible if we can write it as union of two complexes that are d-dimensional and their intersection has to be one dimension less and constructible. Okay? So there are restrictions basically mostly for the intersections. Those are the important. Okay, so in dimension 1, simple complexes are just graphs. And their constructibility is the same as being connected. So these two notions mean the same thing for dimension 1. And there are two important results about constructible complexes. The first one is that constructible manifolds are locally constructible, which means that they are also 2LC and 3LC and 4LC, go on. And that triggered a curiosity whether we can weaken the constructibility assumption for higher values of t. And the second result I have here is the famous Hochster's result that constructible complexes are homotopical. So to answer the curiosity I just mentioned, we defined, as I promised, another movie. So we defined t-constructible d-complexes, again, inductively. So every simplex is t-constructible. A one-dimensional complex is t-constructible if connected. A d-dimensional pure simple complex that is not a simplex is t-constructible if we can write it as union of two t-constructible d-complexes. This time, the intersection has to be, again, d-1 complex, but now we want its d-t skeleton to be constructible. So just to make sure we can all follow, k skeleton of a complex is formed by all the k-dimensional faces and lower. So if we want two skeleton of a complex, we only keep the triangles, edges, and vertices, and everything else. So this is the definition. Let's see what it gives us. Let's take t equals 1. So one constructible complexes, we glue out of two one constructible complexes, and the intersection has to be d-1 complex, whose d-1 skeleton is constructible. But d-1 skeleton of a d-1 complex is just a complex itself. Okay? So for t equals 1, we get the original constructible. And if we jump to the end of the movie, we get t equals d. So let's see what we have. We want the intersection to be d-1 complex whose zero skeleton is constructible. But we just saw a slide before that zero-dimensional complexes are all constructible. That's the base case of the definition of constructibility. So for the case t equals d, we cover all connected simple complexes that are pure. So this interpolates between constructibility and all connected complexes. And I have two more things I want to mention on this slide. The first one is an example. An example of a two constructible complex that is not one constructible. So it's kind of indicated in the picture. We start with a three-dimensional ball that is shellable, so it's very nice. And we take two triangles on the boundary that share a vertex. Like you can see on the picture, it makes a butterfly shape. We only need to make sure that the triangles do not belong in the same vertex. But that's it. We copy this ball and we glue these two copies along the butterfly shape. And I claim that this is too constructible. So why is it? The first part of the definition is clear, so let's have a look at the intersection. It is the d-1 complex because we have a three-dimensional ball, and the complex on the boundary that we use to glue is two-dimensional, so that's good. And then d minus t skeleton, so we have 3 minus 2, which means we need one skeleton to be constructible. But if we look at the one skeleton of the butterfly, it's just a connected fragment. And I mentioned before that connected means constructible in dimension 1. So this whole thing, this whole complex is actually two constructible. And also it is not one constructible, or constructible if you wish. And the reason is we need to know in this case that constructibility is closed under taking links. So every link in a constructible complex is also constructible. But if we look at the link of the middle vertex over there, it will be topologically an annulus. And however you triangulate annulus, it will never be constructible. So this whole complex is not constructible. And the second thing I want to mention here is that we actually don't know, and it bothers us quite a bit, we don't know if these classes are nested. It would be easy induction if we would know the following. If we would know that a skeleton of a constructible complex is constructible. If we would know this, we would have nested classes. But this is not known. There have been some voices saying that they have proof, but I haven't seen one yet. So that's something that is open and definitely worth exploring. What is known is that the same thing is true for shellability. So if we have a shellable complex and we take its case skeleton, it is shellable. It's also known that if we have a Cohen-Macaulay complex and we take its skeleton, it's Cohen-Macaulay. But for this class in between, we don't know. So if there's somebody who would like to work on this, let me know. Okay, another open question for you all. And so using this generalization of constructibility, what we were able to do is to prove the following two theorems. We showed that d-constructible pseudomanifolds are GLC, which is exactly what we're shooting for. And we also showed that d minus t plus 1 skeleton of a t-constructible d-complex is homotopical. So if we take t equals 1, it would say that d skeleton of a one constructible d-complex is homotopic Cohen-Macaulay. D skeleton of a d-complex, complex itself. So that comes down to the famous Hochster's result that I mentioned before. And that's it from me. These are the two open questions I mentioned along the way. And thank you for your attention.
Any questions, comments, or further open questions? I said everyone's thinking.
Yeah. So you don't know where the break is, the exponential.
We don't know, but we believe we are right at the edge. So we think that, so what we were exploring, right? We saw that the links of the d-minus faces are really nice, they're two-dimensional. But if you go one dimension or one t up, if you look at the DLC, you glue things that share a d minus 3 facet, of course, a d minus 4 face, and those have length that is already two-dimensional. So you will have boundary of a ball, and there's so many variations you can do that we believe there will be more than exponential. Yes, but we don't have a proof, and I actually went for 2 weeks to Europe to work with 2 different people to try to prove it, and we were not able to. So,
Did you work on, like, this is kind of going up, perfectly down. Well, like, there's, if you know there's lots of
yes.
Did
So the thing is, so we know that there are more than exponentially many 3 manifolds, right? That's like the general case. However, for those, you allow all gluings. So what we, for instance, we try to lift it up using prisms, but then you have nothing to lift because the gluing on the bottom doesn't have an intersection, so it will not have intersection matter either. So you run into all these technical issues, and we haven't found. Yeah, we were trying to find like a nice extension.
Any other questions or comments?
Can you go over again why the two constructible object wasn't one constructible?
Why it wasn't one constructible? So this this is a ball, right? And you glue these 2 balls together. And if you would be the vertex and you would look around, you would see that the length is just an angle. So it looks like this. Because the vertex will be in bunch of different. So if you have a tetrahedron here, let's say you have a tetrahedron like this, then if this is your vertex, this whole tetrahedron will be in this part, and the length, the part that will be in the length, is the face that does not enter the vertex, so it will be this whole. So you can imagine that you look around this vertex, and you will only see these triangles, and together they will form something like this. And then this is not constructible, because however you will try to triangulate it, you will never be able to get something that is actually connected. So you need constructible intersection, but the intersection you will get will be the reason. Does it make sense?
Anything else? Okay, if not, let's thank Marta. So as a reminder, Chloe is speaking tomorrow.
I will be around till Thursday morning, so. Chat out, so, you know. She's in 755 Computer Bear's office. Where she's from. And the Eve's lecture is at 4. But I think it starts. I'm expecting to be